If I give you two small language models, one with 12 layers and one with 64 layers, which one do you think is better? Most people instantly say the 64-layer model, but a brand new research shows that this answer is very often wrong. And in this video, I'll explain exactly why. What this video is about. This video is based on a recent research article. The goal of that article was very simple, to find the optimal architecture for small language models, not giant models like GPT-4 or Claude, but small models, around 70 million parameters. And what they discovered is surprisingly counterintuitive. Setting the rules, important. To make the experiment fair, they fixed almost everything. All models were trained on the same dataset. All models saw exactly 1 billion tokens. All models had roughly the same number of parameters. The only thing that changed was the architecture. In other words, they changed the shape of the brain, not the food it eats. Two concepts you must understand. Before we continue, you need to understand just two concepts. First, depth. Depth means how many transformer layers a model has. More layers means a deeper model. Second, width, also called hidden size. Width means how much capacity each layer has, how many neurons are inside each layer. And here's the key limitation. The number of parameters is fixed. So if you make the model deeper, each layer must become narrower. This creates a depth versus width trade-off. The first experiment, GPT-2 variants. The researchers first trained 7 different GPT-2 style models. All of them had about 70 million parameters, but their shapes were radically different. Some models had only 4 very wide layers. Others had 64 extremely narrow layers. Between them, 12 layers, 24 layers, 32 layers, and more. Logically, you would expect a smooth performance curve. That's not what they found. The shock, 2 performance tiers. Instead of a smooth curve, the models split into 2 completely separate groups. One group scored around 32% accuracy. The other group jumped to around 38% accuracy. And here's the shocking part. There were almost no models in between. It was either bad or suddenly much better. The hidden size threshold, very important. So what caused this hard split? The answer was not depth. It was hidden size, the width of the model. Every model with a hidden size below 512 failed, even the 64-layer model. Depth could not save it, but once the hidden size reached 512 or higher, performance suddenly jumped. This revealed the hard width threshold for small models. The best GPT-2 shape. The best performing GPT-2 model had 32 layers, deeper than the classic 12-layer GPT-2, but still wide enough to avoid the failure zone. It actually outperformed the standard GPT-2 architecture, so more depth can help, but only after width requirements are satisfied. Comparing different architectures. Next, the researchers compared 12 different architecture families, like GPT-2, LLaMA, Qwen, Gemma, Mo, hybrid design, and the others. Same parameter count, same data, same training setup. And the results surprised a lot of people. They all perform within about 2% of each other. At this scale, architecture branding simply didn't matter much. Good data and sufficient width mattered more than fancy designs. The one big exception, diffusion models. But one architecture broke this pattern, diffusion language models. Unlike autorecursive models that generate one token at a time, diffusion models generate multiple tokens in parallel. The result was dramatic. Diffusion models were 3.8 times faster, about 183 tokens per second compared to 48 for standard models. Even more surprisingly, they showed better factual accuracy, less hallucination, more truthful answers. The trade-off. There is a trade-off. Diffusion models lost about 1.3% accuracy on average benchmark scores, but in return, they gained massive speed and better factual reliability. For many real-world applications, there's a very good deal. Final lesson. So what are the big lessons from this paper? Number 1. For small language models, width matters more than depth. Number 2. Hidden size below 512 is a danger zone. Number 3. Most popular architectures behave very similarly at a small scale. And number 4. Fusion models might be the future for fast small LLMs. This research shows something important. Processing AI isn't always about bigger models. Sometimes it's about smarter architecture choices. If you enjoyed this breakdown, consider subscribing for more deep AI insights. Thanks for watching!